Okay, we're going to start 8.3 here, which is some applications to physics and engineering. In particular, we're going to study two types of applications, which are the hydrostatic force and pressure against a vertical plate submerged in, usually it's water. But and then the next thing is that we're going to study the center of mass. Okay. And by the way, this is the last section that we'll do in chapter 8, okay? Anyway, we're going to start with hydrostatic force and pressure first. It says, one application of integration deals with the force F exerted on a body of water. If you stood on the bottom of a swimming pool, you would feel the pressure due to the weight, which is an example of force, of the column of water above your head. If your head is flat and has a surface area of A square meters, and it is D meters below the surface, then the column of water above your head has a volume that is A times D meters cubed. Okay. The column of water exerts a force. Force is defined to be mass times acceleration, or you can also look at mass as volume times density, and then times the acceleration due to gravity. And so volume is A, density is D, and the volume is D and the density is rho. Okay, where rho is a Greek letter, is the density of water, and g is the acceleration due to gravity. Assume that you're on Earth for these problems. You're not on some other planet or whatever. Okay, so the acceleration of due to gravity is 9.8 meters per square second. Okay. Definition here. Next, the pressure, capital P, is defined as the force per unit of area over the surface of a body. Therefore, to look at pressure, you take the force divided by the area. Force is defined to be A times D times rho times G. Okay, divided by A, the A's cancel there. You got D times rho times G, okay, to get you the pressure of the object. One example of practical application of pressure is with a knife. So if you try to cut a fruit with the flat side, it obviously is not going to cut or not cut well, okay? But if you take the thin side, it will cut smoothly. The reason is because the flat side has a greater surface area. Okay, so there's less pressure, and so it does not cut the fruit. If you take the thin side, then the surface area is reduced, and so it cuts the fruit easily and quickly. Okay, now in this section we're gonna focus on what's called hydrostatic pressure, meaning the pressure of water at rest. Okay. There's another definition there. It says, when calculating fluid pressure, you can use an important law in physics, which is called Pascal's principle. Okay, Pascal's principle states that the pressure exerted by a fluid at a depth d is transmitted equally in all directions. Okay, so figure 1 is illustrating that the pressure at an indicated depth is the same for all three objects. Okay. A common application of this principle is a hydraulic lift used to raise the car off the ground so it can be repaired at a garage. Okay. Figure 2 right here shows a push on a cylindrical piston at point A, and it's lifting, what we mean by a piston is that, it acts like a it acts as a valve that's covering and uncovering parts of the cylinder. Okay, and it's lifting the object at another point B. Now the pressures are equal because of what I just said over here, right? It's at the same depth. So the pressure on point A is the same as the pressure on point B. Okay. Substitute the expression for pressure in terms of force and area to obtain this equation here. So pressure is equal to force divided by area, right? That's what I'm using here. And I'm using that equation there on this other equation to have this statement be true. Okay? And you'd assume that the area is some circular, spot. So substitute pi r squared for the area of a circle and simplify that and solve for the force on point B to have this equation here. Now, since the force exerted at point A is multiplied by the square of the ratio of the radii, okay, and the radius at point B is bigger than the radius at point A, you can see that, okay, then a small force applied to the small piston at A is transmitted to a large force at the large piston at point B. Okay, so ultimately, a small force on piston A can be used to lift a relatively larger weight on piston B. Okay, so I got this a small number multiplied by this thing here, which is equal to a force on B. So if I apply a small force on A, I can use that small force to lift the car on point B. That's what I'm saying there. There's some measurement notes that we're going to need to know in this section that are very important. Okay, in the SI metric system, and there's two systems that we have: the SI metric system and the U.S. customary system. The mass is measured in kilograms, kg, the displacement in meters, m, and the time is in seconds. And the force is in newtons. Okay, 1 newton is the same as 1 kilogram times 1 meter per square second. Okay, in the U.S. customary system, the fundamental unit is chosen to be the unit of force, which is the pound. Okay, so one of the really important things that we're going to have to pay attention to in these problems is what our units are going to be at the end. Okay, like are we going to give our answer in terms of newtons, or are they going to be in terms of pounds? Now we're going to know that immediately just because of the units that are already there in the problem, but still make sure that you pay attention to that. In the SI metric system, the unit of measure for pressure is newtons per square meter, which is called a Pascal. Okay, since this unit is kind of small, the kilopascal is often used. And in the U.S. customary system, the unit of measure for pressure is pounds per square foot. Okay. In the SI units, the mass density of water is 1,000 kilograms per cubic meter. When using U.S. customary units, you write that the pressure is equal to the depth times the density times the acceleration due to gravity. Delta is another Greek letter, is equal to delta times the acceleration due to gravity. Okay, delta is the weight density, as opposed to rho, which is the mass density. Okay, the weight density is already taken into account the mass. So, for example, the weight density of water is 62.5 pounds per cubic foot. Okay, again, we're gonna have to pay attention to what the fluid is in these problems. Most of the time it's gonna be water, but is sometimes not, and so they'll have to give you the mass density or the weight density of another fluid, if it's not water. If it is water, just know that the mass density is 1,000 and the weight density is 62.5. That's me involved in these integration problems. Okay, so then I got the steps for finding the fluid force on a submerged vertical plate. You're going to draw the coordinate axes on the face of the plate and choose a convenient origin. Okay, for a lot of these problems, you're usually going to center the plate right on the y-axis there. Okay, let the top of the fluid be at y equals a. Then a minus y is the depth of the fluid at y. Okay, you're going to have to find the width function, w of y, for each value of y on the face of the plate. Okay, if the base of the plate is at y equals c and the top of the plate is at y equals d, then for when the plate is submerged, then the total fluid force on the submerged vertical plate is given by this integral. Okay, this is going to be the formula that you're going to use in about half of these problems that are in section 8.3. Okay, usually the material that's in 8.3 is kind of split up into two sections here. Okay, your book kind of has it all in one, so this is going to take some time to go through. Okay, but anyway, so again, this integral is going to be the one to know for the fluid force problems that are in this section. Okay, so maybe let's take a look at an example. Problem 1, a tank that is 8 meters long, 4 meters wide, and 2 meters high contains kerosene with a density of 820 kilograms per cubic meter to a depth of 1.5 meters. Okay, so it's not completely full. Find in part A the hydrostatic pressure on the bottom of the tank. Okay, well, let's see. So pressure is defined to be D times rho times G. Okay, well, D is the depth of the water. That's 1.5 meters. Rho is the density. That's 820 kilograms per cubic meter. Okay, and then G, the acceleration due to gravity. Again, assume you're on Earth. So 9.8 meters per square second. Okay, so then the next thing that I'm going to do here is let's go ahead and cancel one of these meters. So I'll cancel this one with one of these cubic meters below. So I got square meters below. And of course, I'll multiply these three numbers. So when I multiply these three numbers, I get 12,054. And that's in kilograms. And I got meters divided by square seconds. And I've got meters squared left over in the denominator there. Okay. So 1 kilogram times 1 meter divided by 1 second, that is by definition 1 Newton. Okay, what I was talking about up here. Okay, so the units here I could say are 12,054 newtons per square meter. Okay. Now, 1 Newton per square meter is defined as a Pascal. Okay, so I can have 12,054 pascals. Okay, and again, since the unit for pascals is kind of small here. 1 Newton per square meter is 1 Pascal, right? That's kind of a small measurement. The kilopascal is used in place of this. Although, for this problem, like I wouldn't care if you had this as the answer as well. Okay. So if you divide 12,054 by 1,000, you get 12.054 kilopascals. Okay, and that'd be the answer to part A. Now in part B, they want us to find the hydrostatic force at the bottom of the tank. Okay, well, force is defined to be the area times the pressure. Okay, so the area of the bottom of the tank, let's see, I got it's 4 meters wide by 8 meters long. That's 32 square meters times the pressure. I just found the pressure in part A, and using pascals. So 32 times 12,054 is 385,728, and again, 1 Newton is defined to be 1 meter times 1 Pascal. 1 square meter times 1 Pascal. Okay, so this would be my answer in terms of newtons. Okay, when we take a look at part C in the next video there, and I'll go ahead and stop right here.